Okay, I think we'll get started. So today we're going to talk about acid-base equilibria. We're not doing any reactions quite yet, but we'll be able to connect very easily here with the ice chart stuff we've been doing earlier, and then the last lecture on these acids and bases. Okay, so if we've got an acid and we put it into water, so we're not going to react it with a base now, we're just going to take an acid, put it into water. So acetic acid, or we're going to do some examples of niacin with this an acid, or vitamin C, which is an acid. That will dissociate, and there'll be an equilibrium constant associated with that, and we call it a Ka, or K acid. So your book may use K acid, your book may use Ka. Likewise, if we've got a base, we call the K a Kb. For conjugate pairs, there's a special relationship. So not these two, these are different acids and bases, but for the conjugate pairs, then Ka times Kb equals Kw. So what that means is for this reaction, the Kb, if we turn this around and say, let's put A into water, then the Kb for this, so let me actually just erase this part. Kb for this is going to be Kw divided by Ka for that conjugate system. Now, if it's a different species, then there's no relationship between Ka and Kb necessarily. Right, for polyprotics, we have two reactions that we write. We have a K acid for 1 and a K acid for 2. So Ka1, Ka2. This is diprotic. If we had triprotic like phosphoric acid, K1, K2, K3. Another thing, we are only going to worry about cases where these are quite different from one another. That allows us to separate the reaction, the first reaction from the second reaction, kind of completely separate it. When you take a course in analytical chemistry, and maybe later in this curriculum, we'll go through complex equilibria, in which we have to worry about these reactions happening simultaneously and of equal importance, and that would be the case when those two Ks are fairly close to each other. But in your book, they'll sort of cherry pick examples where those are quite different so that we can get away with what we're going to do here. All right, so let's just do a monoprotic case first, and then we'll do the diprotic case. So a monoprotic case, let's look at an example for a 0.012 molar solution of niacin. One thing you can practice is your book will have a table of Kas, common Kas, but you can Google this. So it's often very important to know the Ka of an acid, and these are well tabulated for many acids. The molecular formula for niacin is this, and we can think of this, right, as one unit, and that's the acidic protein proton that gets donated, and so there's the separation or the dissociation. Weak acid, so we've got a Ka, and so we just write an ice chart, and this is no different than what you've been practicing. So you're very good at this, and everything works out. We get an X, which is the H+ concentration. For the problems you've been working on, you would just stop there. But often pH is what we use, so that's negative log of that. So we take the negative log of that to get a pH of 3.3. Okay. So very straightforward. Dissociation of a monoprotic acid is just what you've been doing before with the general ice charts. Now, dissociation of a polyprotic, let's look at the pH of a 0.1 molar solution of vitamin C. Now, vitamin C has 2 acidic protons. Here is the formula. And we'll write just the Ka1 piece. So the first proton comes off, is more acidic, comes off, and then the second proton comes off with a Ka2 much smaller. So here's 10 to the minus 12, 10 to the minus 5, 7 orders of magnitude. So this satisfies the condition that Ka1 is much, much greater than Ka2, and we can focus on that first reaction. Another way to say it is, if we're looking for the pH, it's going to be utterly dominated by this hydrogen, this first one that comes off. This is going to be, because this equilibrium constant is so much smaller than this, then the hydrogens that come off of this are going to be inconsequential. And we'll actually calculate that at the end here, or indirectly calculate that. Okay, so just like before, we set up a nice chart. So that's exactly like a monoprotic acid. We're just using Ka1. So we use Ka1 and we get a answer here. And from that answer, we can calculate a pH. Okay. Now, let's go a little further though. What about the concentration of the fully dissociated conjugate base here? So, or fully dissociated acid. So we've lost both protons. So this reaction then would be the one that follows this, right? This will go off and form this reaction. So we've got one of these hydrogens left. That'll come off here and here with a K of 10 to the minus 12. Now, this is something a little bit new here, although you can certainly handle it with what you've learned so far. What are our initial amounts? Well, our initial amounts are what was given to us by the first calculation. And this is another point where we're approximating things, but because of the massive distinction between these two Ks, it's good. So here's our initial amount of this, initial amount of the H plus, right? That's what we just calculated. And how do we know that's the same as this? Well, because it's 1 to 1 mole. 1 mole here, 1 mole here. So the concentrations will be equal. And then we have this, which starts at 0. We haven't made any of that yet in this sequence of reactions. So just to be different than up here, let's say minus y, y, and y. And then this is going to be 0.028 minus y, 0.028 plus y, and y. Using Ka2, we can solve now, and we get a concentration of 1.6 times 10 to the minus 12. And so if we put vitamin C into solution, we'll get a pH of 2.5, which is fairly acidic, but we will get very, very little of the fully dissociated vitamin C. Now, let's take this back and say, well, this is also how much this number, this is y, so this would be put in here. Notice 0.0028 plus 1.6 times 10 to the minus 12, so completely insignificant. And so, to a good approximation, the pH is exactly that. Okay, so this is dissociation of acid into solution. What we're going to do next now is take a little bit of a break, one lecture, and we're going to talk about something called Hess's law. So that will bring us back to some of the thermodynamics of the reaction. We're going to talk about delta H, delta G, and delta S, I guess, for a reaction. And this will help us when we're actually going to react acids and bases. So that's what's coming up. So if you're following through in your book, this will be a little bit out of order with that. In any general chemistry book, this will be. So we're going to jump to the section, wherever that's either before or after, depending on your book, dealing with Hess's law. So that's what's coming up next.